Hello, this is Mohanzad Didia. This is the third module in the book on liquid formulation that utilizes the qubits video format. In this module, focuses on physicochemical characterization of suspension, and it contains two related videos, that is, two submodules. As presented in the first module, the suspension formulation consists of biphasic system. Solid particles are dispersed throughout the liquid phase, in which the solid particles are not soluble. The liquid phase is a single phase in which solids are suspended. Reader is requested to refer to the module 2 for information on physicochemical characterization of monophasic systems. In these two submodules, the physicochemical characterization of solids and sedimentation of solid will be presented. Solids are insoluble in the liquid in which they are suspended. This then makes a biphasic system. Insolubility means interaction within the solvent molecule is far greater than the interaction of solvent molecules with the solute molecule. Solids, there is no dipole-dipole interaction or hydrogen bonding of solute in solvent as shown here. So for soluble system, there would be a dipole-dipole interaction or hydrogen bond interaction. In suspension, there is no hydrogen bond or dipole. In addition to that, vehicle has a low dielectric constant. It has low ability to separate ions into solution. That is polar molecule in non-polar vehicle. So example shown here is D-glucose. Glucose is very soluble in water because of very strong hydrogen bond. The dipole-dipole interaction between a non-polar solvent such as benzene and glucose is very low. Glucose will not be solubilized in non-polar solvents such as benzene, means glucose will form a suspension. In supersaturated solution, sodium acetate is soluble. However, if one uses supersaturated solution, then it will form suspension. The product contains sodium acetate supersaturated solution. A seeding material is introduced and you can see the crystallization of sodium acetate, and this now is insoluble. Excess sodium acetate above its solubility is insoluble. Suspension physicochemical characterization depends on two things. Number one, the particles itself and the vehicle. Suspension contains insoluble particles and its properties relative to the vehicle determines characteristics of the suspension. Suspension will sediment because of gravitational force, and we'll see this in video. Different physical characteristics of the solid in the same vehicle. Solids are added at different particle size, and you'll see a finer material suspending. Slow speed, one can readily see the denser material with a larger particle size settling faster. If we reduce the particle size further, it will take longer time to settle. And now we can see the boundary line of the settlement, where heavier particle or a denser particle settling faster and less dense or finer material sedimenting slower. And one can see that settling of particle and a very clear line is shown. In this case, settling takes over 80 minutes. Classification of suspension is due to the particle size of the insoluble material. Coarse suspensions are generally greater than 1 micron, and it's shown in this photograph. Many theories are written on colloidal dispersion. These suspension size range from 1 nanometer to 1 micron. Then there are nanosuspensions. These are common in pharmaceutical and in cosmetic industry. They appear clear or cloudy. One can see that at the bottom of this slide, nanosuspension. These materials are completely suspended. Suspended particle due to repulsion and attraction of the particles. Usually the solid particles dispersed in aqueous media carries same type of charge. This charge comes either from the particle itself or adsorption of surfactant on the solid surface or adsorption of electrolyte from the vehicle or solution. This charge results into two different forces: repulsive forces and van der Waals attractive forces. The interaction VT between two particles is a sum of energy due to electrostatic repulsion plus energy due to van der Waals attraction. As the distance between particles increases, the repulsion becomes smaller. Attraction between the particles becomes higher, as shown here. The combined energy, V total, then is shown as this graph. At this point, where energy barrier is, that's the maximum total energy of suspended particles. The solid particles on the surface generally have negative charge in aqueous system. That's due to an electrolyte in water vehicle. Negative charge on the particle here attracts the positive charge and the electrolytes that are present, and they form a stationary layer. This is called Stern's stationary layer. Negative charge still keep on attracting more positive and form a second layer. At this layer, there is a potential difference between the particle and the vehicle. In this video, we will see or zeta potential formation. When we suspend material, the suspended material generally has a negative charge due to the liquid. This negative charge in the liquid or vehicle, positive charge starts moving towards the solid's negative charge. This forms a Stern's layer or a stationary layer. This is not sufficient to neutralize negative charge. So negative charge still keeps on attracting the positive charge. This Attraction forms second layer, beyond which everything is neutralized. Diffuse layer let's look at further the effect of zeta potential on suspension. Suspension particles can coagulate depending on its attractive forces, van der Waals forces, or the zeta potential is high enough, it will repel two particles coming close to each other. Zeta potential of greater than 10 degree of coagulation, flocculation is poor, that means they repel. When the zeta potential is close to 0 to -4, the van der Waals attraction forces are predominant and degree of coagulation or flocculation is excellent. We will see this in this video. So there's a negative charge on the particles. If we neutralize that negative charge by adding aluminum sulfate, and positive charge will be attracting to the negative charge as seen here. Within 1 to 2 seconds, the charges are neutralized. As charges are neutralized, flock will start forming because van der Waals attractive forces will now be predominant. So there are two basic characterizations of suspension. One is flocculated, other is deflocculated. Flocculated means they form flocks. As time elapses, particle will settle due to gravitational forces. The settling of the particle, formation of loose agglomerate. Flocculated suspension form loose agglomerates, and this is due to van der Waals attractive forces exceed the repulsive forces. Deflocculated system, electrical repulsive forces predominates. Zeta potential is very high. We'll see that in this video. As can be seen, negatively charged particles, positive charges of surfactant will neutralize it, and flock formation starts. And these flock formation physicochemical characteristics of flocculated and deflocculated suspension is summarized below. Most critical, particles form loose aggregate. In deflocculated suspension, particle exists in suspension as a separate entity. Force of attraction is high in flocculated suspension, that means zeta potential is low. Rate of sedimentation is high because particles settle as a flock. Sedimentation is formed rapidly and sedimentation is loosely packed with a scaffold-like structure which is easily dispersed. So in many pharmaceutical suspension, flocculated suspension is used with a clear label shake well. Flocculated suspension, clear supernatant is observed. Deflocculated suspension, zeta potential is high, particles are repelling each other. Rate of sedimentation is low since each particle settles separately. Since sediment is formed slowly, they become very tightly packed and there's a hard cake at the bottom which is very difficult to redisperse. Suspended material remains suspended for a very long time. Really important in cosmetic products. Polymorph of solids. Change of polymorph or change of one crystalline form to another in suspension can affect its solubility, stability, and clinical bioavailability. Here's an example of ampicillin suspension. Two different forms, anhydrous and trihydrous, and serum concentrations are clearly different, including time at which maximum effect is shown. Chloramphenicol palmitate suspension, polymorph B and polymorph A are suspended, and its bioavailability, clearly there's a significant difference from polymorph A to polymorph B. This is very important to study.